Hi everyone, today we're going to continue our conversation on electrochemistry with 9.9, cell potential and free energy. So the electromotive force is basically the flow of electrons in an electrolytic cell, also known as the EMF. It's basically the potential energy between the anode and the cathode. Electrons are basically pulled from the anode to the cathode. It always goes in that direction. It's always anode to cathode. It does not go in the opposite direction, just like you see in this diagram here. The variable that we use, and we learned this in our last video, is basically called E cell. It's the electromotive force of the cell. We also call it the cell potential. Its units are in joules per coulomb. And again, it's been a while since we talked about coulombs, but a coulomb is the charge where 1 amp of current flows for 1 second. We don't necessarily need to know this too much, but I just want to give you that definition. And you essentially calculate cell potentials using a table of standard reduction potentials. And you do not need to memorize these. You'll always be given these on a problem. So here's a table of standard reduction potentials. It's essentially measured against a standard hydrogen electrode. Who, by definition, has a cell potential of 0. And so all of these are basically measured just against hydrogen. A trend in this is the higher the reduction potential, which we call E red, the more likely the species is reduced. So if you look at this table here, right, we have 2F minus. This is a reduction potential of 2.87. And then over here we have lithium, which has a standard reduction potential of negative 3.04. These are likely to be reduced. Of course, because of this, the lower the reduction potential, basically means it will be oxidized. And again, you don't need to remember these tables. This is something you'll be given a problem. And if you want to find the reduction potential of your entire cell, it's always the electron potential of the cathode minus the cell potential of the anode. And so it's essentially the reduction potential of what will be reduced minus the cell potential of what's being oxidized. And that's how you find the whole cell. One important note here is that it does not depend on stoichiometry. And so you do not multiply by the coefficients in your reaction. You just use the tables right here. So just use the table. Do not multiply it by anything. Now, these standard reduction potentials and the potential of the cell relates back to free energy. As a reminder, free energy is delta G. And so there's this relationship between delta G and the cell potential for an electrolytic cell, and that's that delta G naught is equal to negative N Fe, where N equals the number of electrons transferred, F is Faraday's constant, which is equal to 96,485 coulombs per mole. And E, of course, is our reduction potential of the cell. Now remember, these are at standard state. So basically 1 molar, 25 degrees Celsius, and typically 1 mole of your material. Now in terms of units here, delta G naught is typically in kilojoules. N, which is the number of electrons, is actually in moles because it's the moles of electrons that you transfer. F, I said above, is in coulombs per mole. And your cell potential is typically in volts, which converts to joules over coulomb. Now, something important to note here, right? You have kilojoules and you have joules here, and so sometimes you need to convert to joules. Typically, you would convert delta G into joules, or you would calculate it as joules and then turn it into kilojoules. That's just something to keep in mind when you're doing these problems, that the units do matter here. And now what this basically says is that your cell potential can be used to measure spontaneity, right? Delta G means whether or not a reaction is spontaneous or not, and so does the cell potential. And so these rules naturally fall out. If your cell potential is positive, in other words, E naught is greater than 0, this means it's spontaneous. And of course, that means delta G is less than 0. If your cell potential, I'm going to write cell instead of just E naught, is negative, in other words, the electrical potential of the cell is less than 0, this means it's non-spontaneous. And it means that delta G is greater than 0. And so you can see they are opposites of each other. And so whether or not you're given delta G or you're given your cell potential, you can tell whether or not your electrolytic cell is going to be spontaneous or non-spontaneous. Let's do one practice problem together before the end of this lecture. So in here it says this table provides the half reactions and standard reduction potentials needed to determine if an aluminum fuel cell can be constructed. It says which of the following equations best supports the possibility of obtaining electrical energy from such cell. And so we're essentially looking for which equation will get you a cell that actually works. In other words, one that is spontaneous. And so we got to look at a few rules here. We got to remember the number one rule, that E naught for the cell is always what is being reduced minus what is being oxidized. And for this one, we look for the higher cell potential. So if we look at our two cell potentials here, we have this top one, which has a cell potential of negative 2.31. That's the aluminum reaction. And on the bottom one, we have this cell potential, which is plus 0.4. Of course, we put the higher one first. So E naught of the cell should be 0.4 minus negative 2.31. So if we look at our answer choices here, C and D immediately do not work, right? Because we have the negative being subtracted by the positive, and that is not how this works. So our answer here should be one of those. Now, we've confirmed these first two reactions, which is the electric potential of the cell. Next, we need to look at delta G and see which one of these equations makes the most sense. As a reminder, delta G naught is equal to negative NFE. And you can see here our answers are given in kilojoules, whereas the cell potentials are, of course, in joules. And so what we need to do to this equation is essentially do minus NFE. We have to divide them by 1,000 because there's 1,000 joules in a kilojoule. Now, you can see in both of these, this 96,500 shows up in both because that is Faraday's constant F, and this 2.71 is E naught of the cell, and so they're the same. The only difference here between our two answers is N, the number of electrons. In A, this one says that we transfer 12 moles of electrons. B says that we transfer 4 moles of electrons. And so if we look at our reactions, we got to make sure that they're balanced. What we can see here is that in our top reaction with the aluminum, which is the one that's being oxidized, we have 3 electrons that are being transferred. In our bottom one, which is our reduction, we have 4 electrons that are being transferred. And so for everything to be balanced, we have to multiply these to make the number of electrons equal to each other. To do that, we need 4 on the top and 3 on the bottom. And what we notice is at the end, we should have 12 electrons for each reaction. Therefore, the actual equation that best supports the possibility is this equation E right here. And what you'll see is, of course, E of the cell is positive. This delta G value will be negative. And so for this top one, this will be spontaneous. So that's how you would approach one of these problems. Think about both the equation for the reduction potential of your cell and the equation to calculate delta G from that electrical potential of your cell. We'll do some more practice in class, but for now, that's all. Thanks, guys.